Well, welcome everybody to Chapter 4. We're in the extra class license upgrade class. And Chapter 4 is what we've been building up to. So I'll make a couple of comments. If anybody joins us in the future on YouTube and finds this on our channel, please be aware that we had 3 lead-up sessions to this chapter. For sessions 1, 2, and 3, chapters 1, 2, and 3, I did a little spiel at the end of each one of those that are pretty important before getting into chapter 4. So if you're finding this by accident, be aware of that. And then if I could, I guess we can see all the students now. Just a couple things for my feedback. How many people are watching the Kessler videos? Just wave your hand if you are. A lot. Next, how many have tried to work the calculation examples that we sent out as handouts? Okay, we got about the same number there. That's good. That'll really help you tonight. And then, did anybody actually go back and look at our last presentation of this class? All right, we got a couple there too. Okay, good. And then lastly, how many people are doing the ARRL exam tool to review past classes? All right, good. Yeah. Glad that there's a good number doing that. That'll help us. I sent out an email this afternoon with some comments that might be helpful to you. And for tonight, just have your, well, we'll be jumping around a couple of places, but if you can have your extra class reference sheet handy, we'll be referring to that several times. So I just want to review quickly learning strategies that work. The ones that are circled there, spaced repetition, the exam review tool will help with that. So that'll be effective. And what we're wanting to do, of course, is to defeat the forgetting curve. This thing over here. And spaced repetition is one way to do that. Self-testing and spaced repetition kind of go together if you're using the exam review tool. And then keep at it. It takes time for all of this stuff to sink in, so that's important. We want to wind up with a solid brick wall of learning, which means you just have to keep at it. What you do in between our class sessions is probably as important, if not more important, than what we do during the class. So for tonight, Chapter 4, the first half of it, we're going to be looking at these 3 sections. And you can see that all of the pool questions pretty much are in the 3rd section. In the 3rd section, we're 4.3, Principles of Circuits. We'll be doing about the first half tonight, and then we'll pick up the second half next week. There's a few more questions next week than there are this week, but we're going to do the hard ones tonight. So with that, comment here, we can't really see what's happening with some of this stuff going on in the background. So that's why we need to use equations and math as much as we'd perhaps like not to. Graphs, we're going to be seeing a couple of different kind of graphs tonight. They're pictures of equations, basically. It brings the theory to life. And the 2 types of graphs that we'll be focusing on are, well, 2 of them tonight will be the rectangular and polar coordinate graphs. They do have one pool question regarding graphing that was new in this question pool. So we'll have to take just a minute to explain what they're talking about here. Linear versus logarithmic scale. A linear scale has the same value. We're looking at the y-axis or vertical scale here. For linear goes 500, 1,000, 1,500. It's the same difference between each line. A logarithmic scale typically will go out by powers of 10, 100, 1,000, 10,000. So if you're dealing with large values, like the full ranges of frequencies, a lot of times a logarithmic scale is easier to display the information on. Because this is going up by powers of 10, you'll very often see decibels on this scale, or wide ranges of frequencies. And this is the pool question. The y, or vertical axis, often uses a logarithmic scale for graphs of circuit frequency response. That's because the frequencies are usually such a broad range. It's a lot easier to see it that way. So this was our first appearance of blue text for tonight, so you already know how to answer one question. So let's change gears a little bit and go hiking. So what do we mean by that?
I got the wrong shoes.
You got the wrong shoes. Well, after a while, you'll figure that out because your feet will hurt. So we've got a couple of tools here. We've got a pedometer, it counts your steps, compass, a map. So the first way we're going to consider going hiking is using our rectangular, we're going to compare it to our rectangular coordinate system. And what we're going to do here is we're going to start at one location. I'm going to assume that this is the reference line. And we're going to tell you to go 400 steps to the right and 300 steps up. And that will get you to this point right here. So that's one way we can instruct you to get to a location. The other one is what we'll call the polar method. And for that, we're going to strike a bearing, in this case 37 degrees from the reference, and walk 500 steps. And you can see in either case, we're going to wind up at the same point. And this will be central to a lot of what we're going to be doing with some of our electronics here, because we can represent complex impedance, which we haven't gotten into yet, in either the rectangular or polar form. And each method has an advantage for the kind of problems that we'll be looking at. So the easiest way to see that is this way. Now you may remember back in high school math, the Pythagorean theorem, where it was the square of the adjacent, it's x squared plus y squared equals, or a squared plus b squared equals c squared. So
correct,
you could calculate things that way without needing to do any trig. And because this is set up with triangles, you can see that converting between the two probably would require some trigonometry. Well, we're going to avoid that in the way that we're approaching that. So a little bit more on rectangular coordinates. We've got two axes, x-axis and the y-axis. Point 0, 0 is called the origin. It's right in the middle. And then a data point is identified as an x-y pair. So x, we're going to go over 3, 1, 2, 3, and go up 4, 2, 3, 4. That's the pair 3, 4. Also called Cartesian coordinates, if you remember that from high school. And in our case, we're going to be plotting resistance on the x-axis versus reactance on the y-axis. So how do you remember x and y? And that's important because the pool does make reference to one axis or the other. And here's a little trick that might be helpful to you. If you think of the x-axis as having 2 feet, it's capable of standing on the line. The y-axis is like a fence post. If you try to put that on the line, it would tip over. But if you treat it like a fence post and dig a hole here, then it will hold the letter upright. So x stands on its feet and y is like a fence post. So what you could do to reinforce this, if we practice some repetition, if you can close your eyes for a minute and imagine the x-axis and imagine it standing on the line. Imagine the y-axis being a fence post, and then open your eyes and look at the picture again, and hopefully it didn't change in the process. Now this slide is a bunch of background information. We're not going to see any blue text on it, but this will help prepare us for what's to come. Real numbers are familiar to us. They're like 1, 2, 3, 4, etc. And this is the real oddball, the square root of a -1, defined as an imaginary number because no two numbers multiplied together will give you a negative value. In other words, this can't be solved. So Kastler had some interesting comments. You know, why did they call these? Why didn't they call them weird numbers? Or he had all kinds of interesting things there. But this is something that is used in math. You'll see it in physics and in electronics. kind of a crazy concept, but it is actually useful, and we're going to be using it for reactance, capacitive and inductive reactance. So it's necessary because real numbers don't adequately describe everything in nature. That's why we see these strange things happening. Now, mathematicians use the symbol I, and you may recall that we have an I key on our calculator. Electrical engineers use J because I is used to indicate current. So any place that J shows up in our text or our discussion, when we go to try to solve a problem with a calculator, we'll use the I key. So complex numbers have a real and imaginary part. And it'll really be applied in our case for describing complex impedance in our class and electronics. So complex impedance is resistance. It's the real part, or the x-axis, combined with the reactance, or imaginary part, which is on the y-axis. Now, reactance is not imaginary by any stretch of the imagination, but that's just the terminology that's used here. So how are they indicated? It's real plus imaginary. In our application, it's going to be resistance plus reactance. So any part signified with a leading J on our calculator, it's going to be I. Reviewing some of this we've already talked about. So here's an application, a combination of a 10 ohm resistor and 25 ohms of inductive reactance may be written as a complex number. That would be 10, that's 10 ohms, the real part, and then plus J25. 25 is the inductive reactance. If you look on your extra class reference sheet, I'll put it on the calculator cam, you'll note that for reactance, we're showing capacitive reactance associated with the word negative and inductive reactance associated with the word positive. And we're going to expand on that. Just wanted to point it out. So capacitive reactance is negative. That's why in this first example, inductive reactance is 10 plus J25. For capacitive reactance, which is going to be shown as negative on the graph, the value would be written as 10 minus J25. So that's the concept of positive and negative. And here it is, in case you couldn't see the video, or the calculator cam. We haven't talked about how to work these formulas yet. Well, you know if you worked some of the handouts that I sent you. But the key here is capacitive, negative, inductive, positive on the graph. And we're developing this little by little. So, as I said, reactance is shown on the y-axis. It's indicating positive J minus J. Resistance is shown on the real axis, on the real axis or x-axis. Notice that there's some points showing over here. I mean, there's one concept you can pick up right now, and that's that there's no such thing as negative resistance. So you'll never have any points over on this side because resistance would go to 0 and then start becoming negative. That doesn't happen. So we combine the real and imaginary numbers, real plus J. A couple of examples. So you might be wondering, what happens if the number winds up directly on the x-axis? Well, if that happens, that means it's pure resistance. We don't have any reactance in that impedance whatsoever. Or if the dot winds up on this scale, it's a pure inductor or a pure capacitor, no resistance. And for our purposes, we're going to be considering inductors and capacitors as ideal components. You're probably aware that the leads that are coming off a coil or capacitor will have some value of resistance, but we're going to ignore those. So anytime we talk about inductors or capacitors, we're considering just the inductance or the capacitance, considering them ideal components. Oh, finally got some blue here. A point graphed directly on the axis, directly on the x-axis, represents a pure resistance. No or canceled capacitive or inductive reactance. We're going to talk about how those things cancel in a little bit. A point graphed directly on the y-axis represents a pure capacitive or inductive reactance, no resistance. Only one of those is a pull question, though. Capacitive reactance will be shown with a negative J value, like minus Jx, minus J5, J3, whatever. 50 minus J25 represents 50 ohms of resistance, the real part, in series with 25 ohms capacitive reactance. Everything we're going to be talking about tonight is assuming the series case. There's obviously components connected in parallel, which is another area that exists out there, but we won't be dealing with that. We'll just be dealing with the series case throughout the evening. All right, here's another one. Rectangular coordinates are used to display the resistive, inductive, and or capacitive reactance components of impedance. Now, what is impedance, you might be wondering? That's a combination of reactance and resistance. More on that coming as well. Anytime you see something that has something like Jx in it, it's always going to be rectangular. Now polar, that's the other method. Remember our camping trip or our hiking trip? Well, the way that I like to think of this is that we're looking down on planet Earth. You can see all of these angles coming off the North Pole. So anytime we're talking about polar coordinates, there's always an angle involved. Rectangular is more like a checkerboard. Digging into it a little bit more, the pool has a bunch of terms that sometimes mean the same things. So I'll try to identify those here so we won't get confused. So a complex number may also be represented in polar form. We saw that in our hiking example. You can get to the same destination in either the polar or rectangular approach. Now in polar coordinates, a value has a magnitude and what's called a phase angle. So in this case here, we've got a magnitude of 5. 1, 2, 3, 4, 5. And the phase angle, or the angle from the reference line, is about 53 degrees. You can see it's between 45 and 90. It looks like that's probably pretty close. Other things that you'll see this called are a phasor, a vector or a phasor, and a diagram showing multiple points of impedance is also called a phasor diagram. So you get all of this terminology, and a lot of it just kind of means the same thing. So I'll let you absorb that for just a few seconds here. And then the last thing mentioned is that if there's multiple vectors shown, or phasors shown, they're always at the same frequency. That doesn't come up as a pool question, but that's just something an important point about phasor diagrams. Everything on it is at the same frequency. A little bit more on polar form. If an exam question mentions a phase or angle in relation to impedance, this references polar form. And this can be important in decoding some of the pool questions. An angle is going to mean polar. An impedance is described by phase angle and magnitude. We're taking some of what we talked about and putting it directly into the context of the pool questions. An inductive reactance will have a positive phase angle. Let me just kind of jump back a couple here. There we go. So here we've got a positive phase angle, 53 degrees. Here we've got a negative phase angle. So this would be an inductor, this would be a capacitor. or capacitive reactance. A phasor diagram is used to show the phase relationships between impedances at a given frequency. See, they're coming at this from all different directions, but there's only 2 or 3 principles you have to keep in mind to decode all of them. And a vector or phasor is a quantity with both magnitude and an angular component. So they just keep switching terms around, but don't let that confuse you. A lot of it means the same thing. Vector indicates magnitude and direction. All right, now converting rectangular to polar. And we will need to do this for several of our problems that we'll be looking at tonight. But our calculator is our friend and will help us do that without having to do the pages and pages of trig that are in our book. So traditional conversions use trig. That's page 4-3 in our book. You can ignore that page if you care to. Some calculators can do the conversions directly, like ours. Our calculator is our friend. And we can do something really, really brave now. Let's go over to the calculator cam and see if we can do a rectangular to polar conversion. And the way the problem might be written, it might say, what is the phase angle of this impedance? Well, here we go. In this case, we're going to put in, this is a rectangular form because there's a j there, or an I, 3 plus I4. So I'll turn on the calculator. The first thing we always do is clear it. And the way that we do this entry, it's 3 plus I4. And this is dependent on the way that you've got the mode set. That's why I put out that note this afternoon. So if you get a different answer, let me know. So to put this in, it's 3 plus, now we're going to want to put in I4. Now notice that the pi key is a triple tap key. It's pi, E, and I. A common mistake people make is they'll just tap it twice and wind up with the E. I'll do this slowly. First time we tap it, we get a pi. The second time, we get an E, which is a natural logarithm, which we will not be using. The third tap is the I. That's what we want. 3 plus I4. Now when we press enter, something very magical is going to happen. We come up with 5. This is the angle sign. And 53 degrees is our angle. I see that I shouldn't have put, this is actually a plus.
What
There.
do we want to be in again?
Okay, what you should be seeing is 5.00E0, which is the number 5, and that at an angle of 53 degrees. So did everybody get that?
Yep.
Okay, it's okay to say no. All right, so I'm assuming everybody got that then.
And Dave gave us instructions earlier. You see the mode key there on the calculator at the top.
Yep.
If you push that, there are different the degrees, engineering notation, 2 points of decimal, and then that last one, the R angle 0 or R theta.
Theta, yep,
Zero.
yep, that's that.
If those are set correctly in that form, then this will happen.
Yep.
If they're not set that way, you might get something else.
Yep. So that's what you should have got. If you didn't, the mode might not have been set right. So go back and look at the extra class reference sheet tutorial, page 1. Goes through
Do we
that.
want float?
Say again?
Do we want float?
Float should be at the number 2. I'll go back to the calculator cam and just show you that. So mode, okay, the top line should say degrees. The second line should say engineering. The third line where it says float should be number 2. And then real should be R angle theta.
The float refers to a floating decimal point, which is not what we want for our calculations.
Right, that'll
We
give
want
you
it fixed.
It'll give you a full screen full of numbers that'll just be confusing. And if you didn't get that, that's described in great detail on the reference class, extra class reference sheet tutorial, page 1, that looks like this. which we sent to you and is also in the handouts folder. All right, so very good. Back to the presentation. We've just done our first rectangular to polar conversion, and we didn't have to do any trig. Yay. Resistance versus reactance. And kind of an interesting picture here. Somebody's trying to resist somebody's fist coming at them. So resistance is the opposition to the passage of either DC or AC current. Reactance is the opposition to AC current through an inductance or capacitance. So there's a little, they're both resistant to the flow of current. We've got inductive and capacitive reactance. Then I've got a chart here that a lot of people have found helpful. So the types of resistance to alternating current flow, we've got pure resistance, which we understand pretty well. It's the same as DC. Then we have reactance. There's capacitive or inductive reactance. We'll be getting into more. And then impedance is the combination of reactance and resistance. And these are the symbols. They're all measured in ohms because they're opposition to the flow of current. Only two of them will vary with frequency. If you look on your extra class reference sheet, again, we keep going back to that. The formulas for capacitive and inductive reactance both have an F in them for frequency. So that's why, if we go back to this chart, we see that the value varies with frequency. For reactance, yes, and because impedance is a combination of resistance and reactance, that value will also vary as the frequency changes. So these two are unique to AC value changes with frequency. Pure resistance is the same for AC or DC. So this chart kind of helped tie some of these things together for me, and others have found it useful. So how do capacitors and inductors resist the flow of AC? Well, in the case of an inductor will build up a magnetic field. We'll have more on this to come, but it puts some energy into building up a field around the inductor, and that action resists the flow of AC. For capacitors, it builds up an electrostatic field on the opposite plates of the capacitor, and that opposes the flow of AC. Now, in the general class, we touched on these principles but didn't have any calculations. In the extra, we'll actually have to work some of these. And here are the formulas. I've already mentioned most of this, but I'll just review the units. Now, because this is a direct relationship, remember we talked about direct and indirect or inverse, reciprocal over here, but in the case of inductive reactance, it's going to increase as the frequency increases or the inductance increases. So X sub L is reactance in ohms, got the frequency in hertz, and then the inductance in henries. Normally you won't see henries used, but it'll be millihenries or microhenries. Capacitive reactance operates it's the reciprocal. It's 1 over 2 pi frequency C. And then the units, I think, are self-explanatory. Capacitance in farads, which again we're never going to see, we'll be dealing with microfarads, picofarads, that sort of thing. So we'll have to be using those exponent keys on our calculator. Now here's a graph. Something really interesting happens when you take a particular value of inductor and capacitor and calculate the reactance at a given frequency. So here's some graphs of how, as the frequency is, these are audio frequencies in this case, 10 hertz up to 200 hertz. And at some point, the capacitive reactance graph will intersect with the inductive capacitance graph and meet at a point called a resonant frequency. We're going to be getting into resonant frequency first thing next week. So in this particular case, the combination of these two parts will give us a resonant frequency of around 50 hertz. So something very magic happens when you combine these components. Now we'll talk about the 3-second rule. Gary demonstrated that and talked about it last week a little bit. When we display pool questions, we'd ask people to count to 3 before answering. This has an interesting history, by the way. It used to be little kids would say, well, if I drop my hot dog on the floor, if I can pick it up within 3 seconds, it'll still be good to eat, okay? All right, that's point A. Point B, this has actually been studied scientifically. I don't know why. Somebody had too much time on their hands, but it was demonstrated that when you drop a piece of food on the floor, what is the rate it'll pick up bacteria over time? I don't know if there was a particular time limit there for too much bacteria or not, but it really has some history behind it. But in our case, if we just want to provide a little delay there, it gives your fellow students time to formulate their own answer. Even if they don't speak it, they can be thinking what it should be. People a lot of times will be viewing our recordings, and they like to stop the recording at the end of a pool question and think what the answer should be, and then they start the recording again to hear the answers. So we want to give them time to do it, and that's also helpful for the visually impaired. So those are all reasons we want to wait 3 seconds before spouting off an answer. Now, if you're a contester, you want to give that answer just as fast as you can when the question ends, but we want to give it 3 seconds. Now, there's another thing that we do. You might wonder why. We try to read the question and the answer, correct answer, for those listening and not watching. Some people will actually listen to our recordings in their car while they're driving. Again, visually impaired, this can be helpful. So that's why we will read the question and the correct answer as we go through these. Speaking of answers, what type of y-axis scale is most often used for graphs of circuit frequency response? You can unmute.
Delta.
Delta, logarithmic, yep. Good. Which of the following represents pure capacitive reactance of 100 ohms in rectangular notation?
Bravo.
Okay,
Delta.
it's capacitive reactance. Okay, so capacitive is going to be negative, right? Yep. And the reactance part is going to be the imaginary side, so it would be minus J100 or alpha. Just kind of reviewing what we talked about there, and then applying it. How are impedance described in polar coordinates?
Charlie.
It is Charlie by magnitude and phase angle, magnitude and direction. Which of the following represents a pure inductive reactance in polar coordinates? Pure inductive reactance.
Charlie.
It is Charlie, yes. Positive 90-degree phase angle. Be right on the line there. Good, you're doing great. What kind of diagram is used to show the phase relationship between impedances at a given frequency?
Charlie.
Charlie, yes, phasor diagram. What does the impedance of 50 minus J25 represent? Think about this for a minute. Got a real and an imaginary part. 50, and remember capacitive is going to be negative. So 50 minus J25.
Bravo.
Bravo, yes, 50 ohms resistance. That's the real part. 25 ohms capacitive. That's the imaginary part. And it's negative because it's capacitive. Great. We're going to be building on these things as we go. Where is the impedance of a pure resistor plotted on on rectangular coordinates? It's going to be right on delta, right on the horizontal axis. Yep. Horizontal axis represents resistance, vertical reactance. What coordinate system is often used to display the phase angle of a circuit containing resistance, inductive, and/or capacitive reactance?
Delta.
Delta.
Delta, polar coordinates. Yep. Anytime angle is there, it's polar. When using rectangular coordinates to graph the impedance of a circuit, what do the axes represent?
Alpha.
It is alpha. X-axis represents the resistive component, or the real axis, and the y-axis represents the reactive component. Correct. All right, get into another little area here, electrical and magnetic fields. Electric and magnetic. These components store energy in different ways. Capacitors store energy in an electrostatic field. So here's a capacitor. It's basically just two plates. You could take two garbage can covers if you wanted to and hold them together, and that would be a form of a capacitor. Inductor or coil stores energy in a magnetic field. So in the case of a capacitor, if you put a battery across it, we'll get electrons piling up on one plate. It won't actually be passing any current through because it's insulated in between, but the charge is going to build up across these plates. In an inductor, we're going to create a magnetic field when DC is applied that will be surrounding the coil. So the way that these work in AC, we're going to get to that in a second, this potential energy that's being stored is typically being stored by the device, and then it's given back when the circuit needs it. So the concept of storing the energy, either electrostatic or magnetic, then giving it back to the circuit is going to be central to a lot of things we're going to talk about. So the process of a field charging or discharging will not generate heat. And you might be asking, well, why is that? It's because the voltage and current are not in phase. Much more on that to come. And we can say that a capacitor is a voltage device, building up a voltage across the plates. You can say that an inductor is a current device. You have to have current flowing in order for that magnetic field to form around it. Here's a little bit more. Electrostatic, you have a voltage difference across 2 points. Capacitors store and release electrical energy, and they'll resist a change in voltage. In the case of a magnetic field with a coil, created by moving electrical charges, which means current flowing through the device, they store and release magnetic energy, and they'll resist a change in current movement. Some basic facts about the two fundamental parts we're going to be looking at. A little bit more on the fields. Here we've got, it looks like a magnet with a coil wound around it. The amount of current flowing through an inductor determines the strength of the magnetic field around the inductor. That kind of makes sense. And the applied voltage across a capacitor determines the strength of the electrical field between the plates. Just some more background. Now, there's a couple of stories I'd just like to share here about what happens with an inductor. If an inductor, when current is flowing through it, builds up the field, and it's trying to resist a change in the current flow, what do you suppose would happen if you hooked up a voltage source to an inductor and then disconnected it? Well, what happens is that field collapses instantaneously and quite often will generate a spark that's much higher voltage than the applied DC to it. Back when I was in junior high school, we had a TV, we had a appliance store that sold televisions, and they'd take their old televisions or trade-ins, put it out on their back lot just to rot. And I wanted to collect some of those so I could steal parts out of it. Well, because I was under 18, I had to get a note from home saying it was okay to be out on their lot, so I did that. So I'd take the TV apart, and the power transformer would be plugged into 120 normally, and then have all different voltage outputs. And I'd use an ohm meter to figure out, well, which windings were which. And I was really surprised sometimes when I would disconnect my ohm meter. Just an ohm meter is just that it was an analog ohmmeter, probably had a 9-volt source inside, and when I disconnected it, I got a very nice zap, and that's because of this field collapsing. And I think you had a story too, Gary, didn't you, from your broadcast days?
Over in Liberia, which was my first posting for the Voice of America, we had a transmitter outage, and we determined that the modulation transformer for one of the transmitters was bad. My staff said, well, we've got about 3 or 4 of them down in the basement, but we don't know which ones are good or which ones are bad. So I went down there with my Radio Shack voltmeter on the resistance scale with a 9-volt battery and started measuring windings. And when I released, and it knocked me back because of the counter EMF, that high peak voltage there, I said, that's the one we want right here.
Yep. So those are things that really happen. And just a fast story on capacitors. Capacitors will store a charge for a long time. So I remember one of the things back in high school, or junior high school, actually, electronics class, people would charge up a capacitor, an electrolytic capacitor, maybe 100 volts, and wrap the leads around it so they weren't touching. And then they'd toss it across the room for somebody to catch. Of course, when they caught it, they got zapped. So just some things that I hope I don't inspire anybody to do that. But that's just an example of what's happening with these parts in the storage of energy. All right, principles of circuits. Now we're going to apply some of this. First thing we come to is a time constant. Here we've got somebody holding a stopwatch. So there's RC circuits and RL circuits. We're only going to be talking about resistor, capacitor types of circuits. So what is a time constant? It's the time it takes to charge or discharge a capacitor, and it depends on the values of the resistor and capacitor. And time constant refers to a very specific amount of charge or discharge. This is just here to say that it works with inductors as well. So how does this work? Now, in our book, there's about 5 pages that deals with natural logarithms and lets you calculate the value of voltage for any number of seconds from connecting and disconnecting. There's only one pool question, and it doesn't involve a calculation. It's right here. This is all you need to know. It takes one time constant to charge to 63.2%. or discharge to 36.8, or you can think of that as 2/3 and 1/3 if you care to. So that's all you need to know to solve the one and only pool question in these 5 pages of math in our book. So how does it work? Here's a battery. We're going to say it's 10 volts. There's a switch, a discharge, and in the discharge position, the capacitor would discharge through the resistor. Let's assume that it's fully discharged. So we're going to flip the switch from discharge to charge. So now what's going to happen, we're going to apply 10 volts to the capacitor through this resistor. And because we've got an RC circuit, it's going to take some amount of time because the current will be limited by the resistor. It'll take a while for the capacitor to get up to the 10 volts. So how does that, graphically, how does that work out? Well, this is the charge curve. We're going to throw our 10 volts into the circuit, and slowly, the voltage is going to be rising. This is giving it in percentage, but since we're using 10 volts, this will read out in volts directly. So we want to know when we get to 6.32 volts. That's this point right here. So we're going to throw the switch and click our stopwatch, and when the voltage gets up to 6.3 volts, that's defined as one time constant. So again, read this, see if that makes more sense. Now it takes one time constant to charge to 63.2%. That represents what's called the one-time constant. Going the other way, if we would flip the switch to discharge, the capacitor's made it all the way up to 10 volts, it's going to take one-time constant, this distance are the same, to get down to 3.6 volts. They don't ask us about that though. So that's the concept of what we're talking about here with time constants. There's one time constant calculation, and I'll give you the way that we can solve this. We won't actually do it on the calculator, and then I'll give you a shortcut that makes this really easy. So what is the time constant of a circuit having two 220 microfarad capacitors and two 1 megohm resistors all in parallel? So for something that sounds a little hairy, the easiest way for me to do it is to diagram it. So we've got two 220 microfarad capacitors in parallel, and then two 1 megohm resistors all in parallel. So capacitors add in parallel, so we're going to simplify the circuit to 440 microfarads. Resistors in parallel become less, in this case it'd be half, or 5.5 megohms. So we can do the math from the formula, 440 E times 10 to the minus 6th times 0.5 times E6 to get 220 seconds. Well, that's the hard way to do it. Since micro and mega cancel, one is to the positive 6, one is to the minus, they just cancel. So the 440 times 0.5 is easier, to 220 seconds. And then the shortcut, you'll see that they talk about 220 microfarad caps. Well, the answer happens to be 220 seconds. So that's a real easy one to remember. You don't have to do the math here, but I wanted to show you how it worked. And that's the only question we have like that. And here we are again. Questions. What is the term for the time required for the capacitor in an RC circuit to be charged to 63.2% of the applied voltage or to discharge to 36.8% of its initial voltage?
E.
Bravo.
Bravo, yep, that's one time constant. That's all you need to know to cover those 5 pages of math in our book. Oh, except for this one. This one is equally easy. What is the time constant of a circuit having two 220 microfarad capacitors and two 1 megohm resistors all in parallel?
Delta.
Delta. 220, yep. The 220 appears here, it appears there. Nice to know how to do it, but I don't think anybody's going to bother. That one's so easy to pick out of the question. Now we're going to get into a new subject, phase angle. All right, sine waves related to a circle. Interesting. So here we've got a circle, and it starts out here, and this is going to be 0. Here's 90 degrees, 180, 270, and back to 0 again. So what's going to be happening, this is going to show the relationship between a sine wave and circular rotation. Now there's a lot of reasons why that's important. There's a lot of reasons why sine waves are important. Sine waves appear every place in nature. Waves in a pond when you throw a rock, the vibrating guitar string, sound waves or sine waves, and of course radio waves, and many, many other places. They're everywhere in nature. But in terms of actually generating one electrically, let's take our circle here. We've got, I guess we could call this a phasor. We're going to be rotating it around. And as we do so, we're going to reach 10 volts here, I'll say. 0, 10 volts, back to 0. So at the point A on the sine wave, we're going to be here. Now this vector is rotating, so at some certain point it's going to get to point B, and that'll trace this dot on the wave. Continues around, eventually it's going to get to its peak. It'll describe that dot, and then if you connect the dots through many more points to get the curve to look just right, and it keeps going all the way around. So as we go all the way around here, we're tracing out a sine wave. So there's two ways that we can look at this. One is, let's say that this is happening in 1 second. So this would be at 1/4 of a second. But what else is it? It's 90 degrees. So A, we swing around 90 degrees. So we can describe this point either in degrees or phase angle, or in time that it took to get there. There's a parallel in electrical generation. Here's a reason why this is so important, so useful. If we take that this is a highly simplified picture of an alternating current generator. We've got a loop of wire and some slip rings here, and a negative, a north and south magnet. And as we turn this coil, we're going to be generating an AC voltage as an output. And again, we see what's going on here: 0, 90, 180, 360 in every place in between. Now, phase angle, expanding our terminology a little bit, this would be what's happening with a resistor. This red line we'll call voltage, the blue line we'll call current, could be either one. So when we apply it, a voltage and a current across a resistor, something like this will be happening. Or if we're doing it very slowly with AC like we're showing here, it'll be tracking right with it. So resistors dissipate energy, and voltage and current are in phase. So this would be an AC source connected to a resistor. I said DC, but that wasn't right. Now, weird things start to happen when we switch to other forms of alternating current, especially across an inductor or a capacitor. This is the case of a resistor. Very strange things happen. Remember, capacitors and inductors store and release energy. Unlike resistors, voltage and current waveforms do not rise and fall together with the applied AC waveform. We're going to be talking about Eli the Iceman, another goofy little phrase that will help you solve probably half a dozen pool questions if you understand what it means. First of all, notice that the middle letter of each of those words, Eli and ICE, L stands for inductor, C stands for capacitor. So in the case of an inductor, L, now E stands for voltage, I stands for current. So we can say that for an inductor, voltage leads the current because it appears first in the word. In ICE, current leads the voltage. Okay, well, what in the world is that good for? You're wondering. Well, let me explain one other thing that this can mean. Okay, we said that voltage leads the current in an inductor, or we can say current lags the voltage in an inductor. Both are equally true. The reason that I say that is because the pool questions kind of switch off between them. You'll need to know that. Expanding it a little bit more, just to reinforce it. L is a symbol for inductance, measured in henries. E is voltage, I is current. Okay, those are the statements that come from it. Voltage leads the current, or current lags the voltage, depending upon which one you're looking at. And it will appear both ways, so you need to know that. And then ICE, what again, let's review that. C is the symbol for capacitance, measured in farads. I and E, again, notice these are backwards from the way they appear over here. C is a symbol, okay. So for capacitor, current leads the voltage, comes first in the word, or voltage lags the current. Now, I don't know about you, but I've looked at this for a long, long time, and I still can't do it in my head. If I need to try to figure out if voltage is leading or current is leading, I have to write down Eli or ICE and then look at the word, and then I know I've got it right. Because there's 4 different ways this can happen. Capacitive lead and lag, inductive lead and lag. So I'll just share that. In other words,
Would it be right to say, that you can't have current without voltage started?
yes.
And that current, and that you need current in order to build up a voltage?
Yeah, and we'll come to that in just a minute. Yeah, you need them both. You need them both. But in terms of which one is increasing compared to the other one is going to be leading and one will be lagging. And I'll have a picture of that. So here, this is a variation of what we saw when we were talking about capacitors earlier. We saw that capacitors resist changes in voltage. And then in the DC case, like this, we see that the current will, when you first connect the battery, current will be flowing fairly fast, but the voltage across the capacitor, it takes a while to get up there. And there's sort of a physical example comparison that would be filling a tank with air. So if you've got an air source, big air compressor, and you've got a little storage tank that you use to carry around and fill up tires on your car, What happens when if you start out with an empty accessory tank and you connect your big air compressor in your garage, you'll be able to hear the airflow going like crazy into the tank, but it'll get less and less until the accessory tank gets filled up. So that's a physical example that parallels what we're seeing here electrically. Now things get a little bit more interesting when we get into AC. Now here we had DC, here we've got AC. And the comment about voltage and current both needing to be there, well, that's kind of shown here a little bit. So with capacitor, capacitors, yep, it's ICE, current leads voltage. And the phase angle between the two is 90 degrees. So I'm going to start at this point here, which is maximum voltage. At maximum voltage, we're actually going to get 0 current. Now you're probably wondering, how in the world could that be? Well, with a capacitor, it's resisting the flow of current. So it's lagging a little bit. And as this is happening, it actually turns out to not be, there'd be no current there when the voltage is at a max. And that happens 90 degrees later. So every 90 degrees, you see that these things are changing. Kessler had kind of an interesting diagram where he was showing where voltage and current, when they're out of phase, there's no power being drawn, which is another interesting fact here. I've got a mechanical representation of this coming up. Hopefully we'll have time to show it. But the key thing that you need to know is the relationship between AC current through a capacitor and the voltage across a capacitor is that the current leads voltage by 90 degrees. So here's our current. 90 degrees later, the voltage is at its peak. And that goes on and on and on. A little bit mysterious to understand, but the reason it's happening is because there's a certain amount, I'll call it inertia. It takes a while for the current to catch up to the voltage. Inductors work differently. With DC, when you pass current through an inductor, it's going to build up a magnetic field. Inductors resist changes in current, and a physical example is a flywheel. The flywheel in your car, well, let's talk about a 4-cylinder engine for a second. 4-cylinder engine, you've got 4 spark plugs, and each time a spark plug fires, it's giving a push on what's called the crankshaft that actually powers your car. Now you might be wondering, well, why don't I feel these individual pulses? Well, part of it's because they're happening kind of fast, but the other part is that there's a big hunk of steel inside your engine called a flywheel that smooths that out. So we're giving little impulses to the flywheel, so we're accelerating the flywheel every time a cylinder fires, and then the flywheel tends to keep turning until the next one fires, and it smooths it all out. And an inductor works much the same way. So for DC, current causes a magnetic field to build up around the conductor, and then if the DC diminishes or goes away, like it shocked Gary and I, it'll dump some of that magnetic field into the circuit. So the relationship between an inductor and capacitor are complementary. The back EMF, or induced voltage, and here we have a similar diagram, except in this case, we see that the relationship is just backwards compared to the ELI versus ICE. And this is the animation. I'm going to show at least part of this. I just found this yesterday, and I thought it was fabulous. Okay, here it is on the board. We got that going out, Gary?
You have to hit play.
I know. I want to put on my earphones so I can hear it.
Certain points over here. There are some points over here, as you can see, where voltage is 0 in the circuit, 0 voltage, but we have current to be maximum. How does that make any sense?
Right.
And then you have these points over here where the voltage is maximum in the circuit and the current is at 0. I mean, what's going on? And if you think also, there are points where over here voltage is negative but current is positive. I've never experienced anything like this in our previous circuits. So I'm really trying to figure out what's going on over here, how to digest this. Luckily, I found a mechanical analogy. So here's what I mean. Here we have our current and voltage oscillating one more time. But what we'll do now is we'll imagine the voltage to be similar to height of a plank above the ground, which is pivoted to something that's connected to a wall. So the plank is free to go up and down, let's say. And the voltage represents the height of that plank. So an oscillating voltage, let's concentrate on that, can be imagined to be an oscillating plank going up and down. Okay? All right, and for the current, what we'll do is we'll imagine there's a box kept over here. And the box is going to slide, and we'll assume there is no friction because it's a pure resistance-less circuit, right? It's a pure only inductor is there. So inductance is like the inertia. The box's inertia represents the inductance, and the box's speed represents the current. What I want you to do before I show you the animation is I want you now to consider the speed and the height and look at their relationship and see if that follows the same current and the voltage relationship. Think about when the speed of the box would be 0, when would it be maximum, when it would be, when would it be 0 and maximum, for what heights. So imagine right now I've just kept the box and you imagine the thing goes back and forth. So just visualize this yourself first. All right. So right now the height is maximum and I just kept the box. My question is, what's the speed of the box? Well, because of its inertia, it's going to be 0. It'll take some time for it to pick up the speed, right? So we have a situation where speed is 0, but the height is maximum. But now let's wait and see what happens. As the plank goes down, notice the box will keep on picking up speed. It'll pick up, speed keeps on increasing until the plank becomes parallel to the ground. That's when the height is 0, but the box now has a lot of kinetic energy, a lot of momentum. It'll have maximum speed. After this point, the plank will go down, but the box will not immediately come back down. Because of its inertia, it'll continue to keep going up. So even though the voltage is negative, the speed or the velocity stays positive. Ooh, does that make sense now? Let's look at the animation. And as it goes up, it starts losing its momentum. And eventually, when it comes to the negative height, negative maximum, that's when the speed of the box goes to 0. Very similar to what's happening to our circuit, isn't it? Beautiful, right? I love this analogy. It helps me digest what's going on. And let's now look at the same thing with the arrow mark. The arrow mark of this represents the speed.
So this continues. I'll stop it here because we're limited for time. But I do have the link on our page.
Just like a metronome.
Yeah, kind of, and it's delayed by about half. Trying to get my mouse back here. Mr. Mouse, where did you go? Here we go. Okay. Slideshow, current slide. All right. There we go. So here's the link. Now the first 6, almost 7 minutes of this video are all math. Most of you aren't going to be interested in that, but from 6:54 through to the end is this animation and more explanation, I can't talk, of how this is working. And the key point to me was the inertia that is there, both to get the box started and to keep it going after the voltage swings back through 0. And this exactly parallels what we see in this diagram. I never saw anything like this before. I just found it yesterday, so I wanted to share that with you. And you might want to look at the rest of that because it's very good. So in inductors, we see the same kind of stuff. The phase angle's 90 degrees. And ELI and ICE are at play. And during an AC cycle, we're storing and releasing energy twice per cycle. Here's the positive peak, here's the negative peak. And we're seeing the voltage peak and the current being offset by 90 degrees. And with that animation, you can kind of see what's going on. And the reason that phase shift exists is because of the inertia of the device opposing the flow of current, either capacitor or inductor, operating, of course, electrostatic versus magnetic. And then right into some questions. I skipped over those last ones pretty fast because I think the animation kind of explained it. So what is the relationship between the AC current through a capacitor and the voltage across a capacitor? And I'm going to tell you something. When you get this on your test, this won't be written on it, okay? I got to turn my laser pointer back on. Yeah, this won't appear in your test. I just did that to help you. And like I said, I have to write this down on a piece of scratch paper or I get it messed up. So again, what is the relationship between the AC current through a capacitor and the voltage across a capacitor?
D.
Did you say Baker or?
D.
D, yeah. Delta. That's correct. Current leads voltage by 90 degrees. Good. And remember 90, that's important. What is the relationship between the AC current through an inductor and the voltage across an inductor? Inductor, so we're talking ELI.
Bravo.
Well, inductor is L. Okay, that's why I have to write this down, because I screw it up if I try to do it in my head, because there's four different possibilities. So inductor, voltage leads current by 90 degrees, A. Don't write that in your test booklet, though, or they'll make you pay for it. Scratch paper, or put that on your memory dump sheet. All right, and here's the picture of what we looked at. We got pure resistance, reactance, impedance being the combination. This is the same chart that we saw before. Now we're going to jump into another aspect of complex impedance. All right, impedance, Z, is composed of two components, resistance and reactance. I thought this was kind of an interesting cartoon. Here we've got a professor trying to tell everybody how simple this is, and we've got somebody looking outside the box and seeing how complex the real world is. I thought that was very applicable to what we're talking about. So reactance can be either inductive or capacitive. Right? Resistance and reactance may be connected either in series or parallel. Our cases tonight and in this chapter are going to be in series. A little bit more. The little look sign on the bottom. Are we positive or negative? Are we capacitive or inductive? Okay, the phase relationship between the current and voltage can be between 0 and 90 degrees or between 0 and negative 90 degrees. Again, depending upon if it's inductive or capacitive. The phase angle depends on the relative amounts of resistance and reactance. We saw that the phase angle was going to be 90 degrees for a pure inductor or minus 90 degrees for a pure capacitor. It'll be somewhere in between 0 and 90 if there's resistance in the circuit. The sine of the angle depends on the type of reactive element. We've said that a couple times already. Inductive reactance, positive phase angle. Capacitive reactance produces a negative phase angle. So how do we solve some of these kind of problems? So we're going to have some components that we'll say are inside this black box. We've got an input and an output. We want to come up with some answers to our problems of what's happening inside this black box. So if there's multiple resistors involved, we're going to combine them into one resistor. If there's multiple reactive elements, one capacitor, one inductor, let's say, we're going to reduce that to one reactive element. We know that we have opposite phase angles. And then if we combine the capacitors and inductors, they'll result in a total reactance that's different. In other words, what's happening is if you've got an inductor and a capacitor, whichever one is dominant, whichever one is biggest, will be reduced by the value of the smaller one for a smaller total reactance. If capacitors and inductors have equivalent reactive values, they will cancel each other. Phase angle will become 0, resulting only in a resistive element. So we're going to have one here. Going to work through this one. We're going to calculate the impedance of this inductor. So we're going to have an AC signal here. We're going to have a 1 kilo ohm resistor, a 20 millihenry inductor. And we want to calculate the reactance of the 20 millihenry inductor at 10 kilohertz. So we'll go over to the calculator cam. Get the right card out here, which I've managed to lose my cards now. Here they are. Turn on the calculator. So here's our problem. It's the same one that I just described there. And if you look at your your extra class reference sheet, we'll see that the formula for inductive reactance is 2 pi frequency L. The phase angle is going to be positive. So here's our formula. So XL, which is what we want to solve for. So on the calculator, we're going to enter, there's our formula, 2 pi. So 2, did I clear first? Nobody challenged me. 2 pi. Now the inductance is, oh, okay, I just confused myself. This is what we're trying to solve for. So it's 2 pi and then the frequency. Okay, the frequency is 10 kilohertz. Okay, so 10 kilo is times 10 to the third. What's EE 3 times L, which is 20 millihenries. Milli is times 10 to the minus 3. So we have to use the negation key, not the minus key, the negation key. Exponent, yep. Negative exponent, 3.
You did not hit enter exponent though.
I'm going to clear this. Thank you. Do it over. 2 pi. Thank you for watching me. Frequency, 10 kilohertz. 10 EE 3 times, now I'm going to do it, 20 millihenries. 20 EE.
There you go.
The negation key, millis times 10 to the minus third. Enter. So we came up with an answer of 400 pi. Now that's really useful, isn't it? All right, so remember our answer toggle key over here? Press that. And now we get 126 E3, or about 1260. Or if you want to see it expanded, hit the answer toggle again. Now we get our 1256, which is the correct answer, 1256. So that's a way that we can calculate the complex impedance for this circuit. And turn this off.
It wasn't the impedance of the circuit, it was the reactive.
The reactance, yeah, that's actually on the next card. We're going to continue this. Okay, now we're going to actually get the impedance and phase angle, just to kind of walk through how this works. So we know that the resistor is 1,000 ohms. We know that X sub L is 1256 from the previous slide. So now we can actually, we can enter this in rectangular form into the calculator. So that's, I'm going to clear first. 1,000 plus, now we have to put in I 1256, and be careful, okay, it's the pi key, that's once is pi, twice is E, don't stop there, hit it again for I. 1,000 plus I, 1256, and then press enter. And then we get, this winds up to be about 1605 with a phase angle of 51.47. It's an inductor, so that phase angle is positive. And we know that this is an inductor, so voltage is going to be leading current. Now several pool questions will ask us to do these kinds of things. Turn that off and come back here. This is just a review of what we just did. And then some questions. All right, see if we can see if we can remember any of this now. What is the phase angle between the voltage? What is the phase angle between the voltage across and the current through an RLC circuit? If X sub C is 500 ohms, R is 1 kilo ohm, and XL is 250. Is that the one I have on the board? Yeah, it is. Okay. So I'm going to come over to our blackboard. I've got this diagram. It doesn't matter what order any of these things are in. And what I wanted to demonstrate here is how we take the next step in a case like this. So my first question is, of inductive reactance and capacitive reactance, which one is dominant? Well, the dominant one is going to be the bigger one, or 500. So 250 ohms of that 500 is going to be canceled by the inductor. So we're going to wind up with an equivalent circuit here of 1,000 ohms and 250. And it's going to be capacitive because capacitive is dominant. So that's the way you simplify one of these. You can diagram it, or this you could probably do in your head. You could look at this and say, okay, capacitance is dominant, but we're going to reduce, because it's bigger than inductance, so we're going to reduce it by the amount of the inductance, leaving us 250 ohms of capacitive reactance, and the resistor is still there. So now we can go to the next step. So with that, let's, let me see if I had the, well, that turns out to be the answer. Okay. So just reviewing what we did here, this was our circuit. Draw it and show the values. And it's asking for phase angle, and if it's leading or lagging. So is X sub C or X sub L dominant? We decided it was X sub C, the capacitor. We reduced the larger by the smaller. So we started out with negative 500. We reduced that by 250, resulting in 250 ohms of capacitive reactance, because it was dominant. And then we can enter it in rectangular form. And we'll go do that on the calculator. Clear always. So 1,000 minus I250, 1000 minus I, triple tap the pi key, 250, enter. And the problem was only asking for the phase angle. So the phase angle turns out to be 14 degrees. It's actually negative, but they're just interested in basically the absolute value of the phase angle, but 14 degrees is our answer. So back to the slide, press enter, and we get a phase angle of 14 degrees. And the pull questions don't ask if it's positive or negative as we get into those. So using ICE, capacitor, voltage is lagging the current. Okay, and the way this pull question is set up, it's asking for the lagging rather than the leading. So let's jump back to the question now. 14 degrees with voltage lagging the current. So we just walked through the steps of how we got there. Here's another one, and we won't actually go through and calculate this one because it works exactly the same. You have to ask the same questions. Which one is dominant? X sub C is 300 ohms. X sub L is 100, so X sub C is going to be dominant again. It's going to wind up being 200 ohms, negative, and we plug it in to our calculator the same way. And here's the steps if you want to do that on your own, but it's exactly what we did with the previous one. And here's the third one, so there's 3 of these. Now, if you're not allowed to use a calculator in your exam to do conversions, you might have to memorize these. Exactly the same steps. And then we're going to get to a different flavor of question, where it asks which point on figure E5-1 best represents the impedance of a series circuit consisting of a 400 ohm resistor and a 38 picofarad capacitor at 14 megahertz. Well, the ones we've seen so far, they just gave us the capacitive or inductive reactance. In this case, we're going to have to calculate it because it's not given. And I'm going to share a few tips here right off the bat. We know we can't have negative resistance, so in the answers over here, we know we're never going to have anything to the left of the y-axis, so it can't possibly be 0.5 or 0.7. Okay. The other thing that I'm going to suggest that you put in your head, you notice that 0.8 and 0.6 are very close to the x-axis. Let's pretend that they're on the x-axis. So none of the answers are actually going to be one of these. So that just leaves 4 possible answers. That's going to be a shortcut that will let you solve these without having to do the calculation, but we'll calculate the first one. So it's going to wind up being 0.4. I'll show you why. So it's asking which point. We need to know the resistance and the capacitive reactance. This is a capacitor. We need to draw it and show the values. Calculate x sub c. Remember, x sub c is 1 over 2 pi frequency c. You get to memorize that for next week, by the way. At any rate, it works out to 299 ohms. You write it in rectangular form, 400 minus, 400 ohms resistor, 299 ohms of capacitive reactance. And then we get to match it to the point in the question. So it might be a little bit hard to see this. If you look at page 421 in your book, there's a bigger version of this. I'll use this just to carry us along. So it's going to be 400 minus I 299. So we're going to go over to the 400 point, which is right here, and then we're going to go down because it's negative to 300, basically 299. So it's got to be 0.4. Now, did it work out? Yeah, 0.4. Okay, now I'm going to show you a shortcut, and we can skip solving the next 2. All right, so it's a 400 ohm resistor and a 38 picofarad capacitor. So we know the 400 is going to be good. We know that, and we know it's a capacitor, so it's going to be negative. Well, look here, there's only 1 point on the graph that is negative, so it has to be 0.4. So we can get to the answer to this one without having to do any calculations. Remember, I told you it can't be anything to the left of the y-axis, and we're going to put the 0.8 and 0.6 right on the axis. It'll never be one of those. So do you suppose that the next 2 questions could be that easy? Is there any chance of that happening? Okay, we went through it all, and we wound up with 0.4. Okay, this is the one we just did. Okay, and this is the next one. Okay, E5C11. All right, so in this case, we got a 300 ohm resistor and an 800 microhenry inductor. We have no idea what the inductive reactance is, but we know it's going to be positive because it's an inductor. So we got 300 over, can't hardly read these little tiny numbers. Here we go, 300, okay? And then it's going to be positive, so it's pretty much got to be 0.3, right? And it is. All right, well, there's 2 of them we could have solved without doing any math. Is there any chance the third one could be like that? This is the way that you, back it up. All right, so this is the third one. 300 ohm resistor, 19 picofarad capacitor at 21.2 megahertz. So 3 over, so we know it's going to be here, and there's only 1 that's negative, down here, 0.1. So they were real nice to us. If you use my shortcut, you can do all 3 of these point problems without having to do the math. But I did give you the method of doing it in each case if you want to walk through it. Now we're going to take a break at this point, and then finish up the rest of this chapter. So next will be admittance and susceptance, and look at these people here. So 5 minutes, take a break, stretch, let your mind cool off. We'll be back in 5. Okay, we're back. I hope you did something fun during your break and ready to engage for about another half hour, and then we'll be wrapping it up. Now, there's 5 pool questions on admittance and susceptance. This is something that I have never needed in my ham radio career, many years, and you probably won't either, but there are 5 pool questions, and they're kind of super technical, okay? To really understand how these work would take a lot of background and study. So I'm going to take a little bit different approach. I'm going to cover the highlights and give you some memory tricks to give you the best possible chance of getting 100% on your exam if you get any one of these 5 questions. So here's some interesting graphics. We've got a fellow standing in a door, and we've got this mean-looking guy and terrified-looking woman. Let's see how all of that's going to fit together. We'll take a look at the extra class reference sheet just quickly. You notice I've got a section down at the bottom called aids. And here at the very bottom I've got impedance, admittance, reactance, susceptance, and one of the facts. So we'll be expanding on some of these here. We've already looked at ELI the Iceman and direct and inverse relationships. So from the extra class reference sheet, we've got the impedance section, reactance section. So memory tricks. Pool questions use the words reciprocal and inverse. That means the same thing. So just don't let that throw you. Somehow or another, we need to associate impedance with admittance, okay? Because that's one particular formula. When I say formula, it's just basically the equation. We don't have to actually plug in any values and solve anything for this, but we need to associate impedance with admittance. The way I do that is with a door metaphor. A door, when it's closed, you are impeded from entry. If it's open, you may be admitted. So impede, admit. That helps me keep those two associated. Now, converting impedance to admittance in polar form. This sounds really hard, but I'm going to try to help you with some memory tricks to do it. Okay, converting impedance to admittance. Okay, you take the reciprocal of the magnitude. Okay, this is the impedance, so whatever value that is, 20 ohms, the reciprocal is the admittance, okay? So that's what all this is saying. Take the reciprocal of the magnitude, okay, and change the sign of the angle. So if it's angle, that's going to be polar. And the way the pool question is worded, polar does appear in the pool question. So the sign of an angle will flow together with that. And then you have to be careful because one of the distractor answers, meaning one of the wrong answers, says just the opposite of that, which means it says take the reciprocal of the angle and change the magnitude. So don't be tripped by that. So that's the impedance side. The reactance side, all right? Memory tricks. First of all, we need to associate reactance with susceptance, or this piece of the formula. And I've got this little story about Suspicious Bob. This is Suspicious Bob. He looks like not such a nice guy. And Mary over here is really afraid of him, okay? So let's see how my silly story flows here. Bob is suspicious. Mary reacts to Suspicious Bob. Bob is suspicious, and Mary reacts. The initial of his first name is B, all right? Well, susceptance is B. The pool asks us about that. Now, Mary doesn't have to worry about Bob because he's really imaginary. Again, my silly story. So there's another pool question that wants us to know that susceptance is the imaginary part of admittance. Admittance is way over here. But if you can get in your head that Bob is suspicious, Bob is only imaginary, that might help you get this one right. So the way the pool question works here, convert magnitude of reactance to susceptance. Well, first of all, we can see that it's going to be reciprocal. That's easy. And notice that the word polar doesn't appear here. So there's nothing to do with angles. One of the distractor angles, distractor answers has an angle in it, so don't get tripped by that one. This one, the question does not have polar in it, so it's not going to appear in the answer. So these goofy little tricks might help you get through these without understanding how the math works. It's extremely confusing in the license manual, and it's probably even more confusing if you go to Google and try to figure this out. Now, susceptance and admittance do play a part in engineering, and Gary might be mentioning those when we get to the Smith chart, because they do have a use, but I'm guessing you will never need to do it.
It has to do, we've been talking about series, and then we'll be talking about parallel. And so that's where the admittance and susceptance comes in the parallel universe.
Yep, the parallel, yeah, and everything we're talking about this chapter is series. Okay, so admittance is the inverse of impedance. You saw that here. Converting impedance to admittance, reiterating some of this. In polar form, and look for the word polar, take the reciprocal of the magnitude and change the sign of the angle. There's an angle involved because it's polar, so maybe those words will help you recognize it. Susceptance. So what is susceptance? It's the imaginary part of admittance. Bob is imaginary. The effect of pure reactance magnitude when converting to susceptance is just replaced by its reciprocal. You notice the word polar doesn't appear here, so it's just reciprocal. B is the letter commonly used to represent susceptance. Suspicious Bob. Okay, so those are my silly little tricks to help you. How is the impedance in polar form converted to an equivalent admittance? Everybody's thinking there. I went through that kind of quick.
Bravo.
It is Bravo. It says polar, so there's going to be some kind of a sign reversal. Take the reciprocal of the magnitude and change the sign of the angle, because it's polar. What is the effect of the magnitude of a pure reactance when it is converted to susceptance?
Delta.
Delta. It's just the reciprocal. What is susceptance?
Harley,
Bob is our imaginary friend. Yes. What is admittance? A door will have two functions. You do associated alpha, inverse of impedance, right? Yep. So if you can keep admittance and impedance associated, you know it's the inverse, and then hopefully it'll jump out at you. What letter is commonly used to represent susceptance?
delta,
It is delta. And you notice my caution here, don't confuse the letter of the answer with the answer, because there is a Bravo as a letter. All right, and these will probably be different on your exam if you get it. Now, of all of these goofy 5 questions, you could only possibly get 1 on your test if you get any. Good. Now, reactive power and power factor. We're approaching the end, which is good. Used to be there were about 7 or 8 questions on the poll. Now there's only 1 or 2, and they're real easy. So another concept that's worth knowing about. Now with power in a DC circuit is voltage times current. Remember your PIE chart? Power equals voltage times current, DC circuit. Now apparent power, this is a new concept for AC. Now remember, inductive and capacitive components are reactive, and reactive components don't consume any power. So let's see how that comes into play here. So with apparent power, it does not take into consideration the phase angle of reactive components. instead of expressed in watts like it would be up here, voltage times current, it's expressed in terms of volt amps, volts times amps, which is not the same as power. So reactive power is wattless, non-productive power. Reactive power, there's no power that's consumed by a capacitor or an inductor. That's why this is true. Reactive power in an AC circuit that has both ideal inductors and ideal capacitors is repeatedly exchanged between the associated magnetic and electric fields, but is not dissipated. That is just kind of a way of saying the same thing as this one, but these are two separate pool questions. And the relationship between voltage and current for reactive power, they are 90 degrees out of phase, just like we saw before. But in this case, we're talking about power that would be drawn from your house, and 120 volt power, for example. So here's an example. We won't have to, I guess this is one that shows up in our pool. So here we've got a 100 ohm resistor. We've got a 100 ohm inductive load of some kind. Maybe it's a motor, 100 ohms, current of 1 amp. Now and a voltage of 200 volts AC. So you would think that current, that you'd be able to solve this by combining these. Well, you can't, because the inductor does not consume any power. So the only thing in the circuit that's going to consume any power is the resistor. So 200 volts AC times 1 amp, we're going to have 200 volt amps. 200 volts, we got 1 amp, that's 200 VA. 1 amp indeed flows through both XL and R. Current and voltage are not in phase through the inductor, so no real power is consumed by the inductor. Real power is consumed by the resistor only. So the formula for power is I squared R. I is 1 amp, R is 100 ohms, and that gives us 100 watts. Remember, we had 200 volt amps, but we only have 100 watts actually being dissipated. Inductor consumes no power. Remember, it's wattless, non-productive power. So the real power is 100 watts. Apparent power is 200 volt amps. And the power factor, we won't have to calculate any of these, but it's 0.5 is the real over the apparent power. So this is the only calculation question, and it's going to be real easy, and I'll show you why. What is the, in a second, what is the phase relationship between current and voltage for reactive power?
Charlie?
It is Charlie, 90 degrees out of phase, and that's just for the reactive element, which is kind of what it says here. Okay, the next one, what happens to reactive power in ideal inductors and capacitors? What happens to the reactive power in
Bravo.
It is Bravo. Yep. Energy is stored in magnetic or electric fields, but power is not dissipated. How much real power is consumed in a circuit consisting of 100 ohm resistor in series with a 100 ohm inductive reactance drawing 1 ampere? And this is the one that we looked at, so you may remember.
Bravo, 100 watts.
100 watts. And the shortcut to this one, we have 100. 100 appears twice in the question, and 100 happens to be the answer. So you can either use the I squared R thing to get 100 watts, or just line up the 100s to get that one. What is reactive power?
Delta?
Delta, wattless, non-productive power. No watts are consumed by the reactive components. Oh no, I can't believe it. We're at the end of chapter 4. Oh, let me add one more thing. Power companies hate reactive power. You know why? The reason is they have to generate to to take that load. So they typically have humongous capacitor banks at substations to counteract that reactance, or in major industrial complexes, sometimes they'll do that. So that's it. So this is, we're a little bit early. Now I wish we would have looked at the rest of that video that we were looking at with the plank and the box and all of that. But you can look at that on your own. And this is a time when we slip over to what Gary calls class chat. We'll do that. So any questions that we have for anything we've covered any place here or tonight in particular?
I'm gonna have to recover it again.
Well, yeah, I did go through some of that pretty quickly. So going through it again would probably be helpful. But I think with the examples, if you can follow through the examples and duplicate them on your calculator, you do that once or twice, and before long you will own it.
Just out of curiosity, how much of this do you actually use as a ham?
Well, as I said, the impedance and susceptance, never. Some of the rest of it will build into some additional concepts. For example, we're going to get into resonant frequency next week, which radios, and all of ham radio, the concepts of resonant frequency and bandwidth and those kinds of things you'll use all the time. And their foundational information, the foundational material that allows them to work, are those inductive and capacitive principles that we talked about tonight. So that will be useful. You might not have to calculate them, but if you can relate to what they are, it'll make you a much better conversation partner.
Thank you.
Yeah.
Going back, I'll ask the question later once I formulate it better. Thank you.
Okay, and we're always available through the week. Sometimes it takes me a while to get back to people, but if you ask a question and I don't reply to your email, get me again. I get over 100 emails a day from all different places, so it's easy for them to get lost. But I really want to be responsive to our class, so bug me if you don't hear from me.
Thank you.
Please feel free to ask questions. Myself, Gary, we'll try to help.
All right.
Appreciate you guys.
Well, yeah, well,
Thank you.
yeah, we
Alrighty, well, they've been a good class. We can let them out early tonight.
Oh, wow. Yeah, that means I get paid less, but that's okay. No, we don't.
Yeah.
We don't take any money from this at all. That was just a joke. Okay.
All right.
Alrighty, y'all.
See y'all.
Until next
Take
week.
care.
Watch for
Bye.
an email from Dave.
Yep.
73.
Bye. 73.